Welcome to this presentation on improved estimation accuracy in OFDM-based joint communication and sensing through Kalman tracking and interpolation. My name is Charlotte Muth. This was joint work with Leon Schmidt, Srinivas Shimalgi and Laurent Schmalen. Let's start with our motivation. We consider joint communication and sensing as a type of radar-like sensing in a communication network. Also, we apply a uniform linear array at the receiver and at the transmitter so that we can also estimate the angle of arrival of our signal. So by estimating the range, velocity and the angle, we can solve common JCAS tasks such as localization of a target, such as this deer shown here, and tracking of such a target that is just reflecting the signal transmitted by our base station. Simultaneously, we can also communicate with some type of user equipment. Our scenario is very much bandwidth limited. We choose quite a small bandwidth for our carrier frequency and our frame duration here. Why? Well, we want to explore this setup here where our bandwidth truly limits our range resolution. So currently we have here this nice deer. Now if we look at a true trajectory, as here shown with the blue circles, we see that we get some gradual movement, but from the measurements that we get from these axes, we see that it jumps around quite a bit and the accuracy is limited. So our range accuracy is only 6 meters in this scenario. There are multiple ways how to improve this accuracy, though we'll first go through the system model. So we first have here our usual transmitter, so we have some OFDM modulation, and then we also apply beamforming for our target but also for our communication device, which isn't really addressed in this talk that much. So we transmit a signal, then it's reflected by the target, which again is our deer here. Then we receive it with our multiple antennas, estimate the angle from that, apply receive beamforming, then estimate range and Doppler from the composite signal and afterwards also apply tracking. And then we get an estimate for range, radial velocity and our angle of arrival. So in our signal model, this means we have a receive signal at each antenna K, which is subject to attenuation, for example, from the radar cross-section, so the attenuation, but also the path loss. Then this epsilon here is our transmit signal, and we get some time delay. Then we also get a Doppler shift from the movement of our target. Then additionally, this phase shift, which we get which is different for each antenna. So we can estimate our angle of arrival and then some noise. So for angle of arrival estimation, we use the Bartlett method, which is just based on the periodogram on the last 100 samples to have the complexity really low and to get like a very quick angle of arrival estimate to also perform the receive beamforming afterwards. Then we apply the receive beamforming, and afterwards we get now into the range Doppler estimation. So from our receive frame Z and the transmit frame X, we perform a element-wise division, and then we apply a 2D FFT basically to get our range Doppler matrix. And afterwards we apply our peak power detection. Now we see here the first way how we can improve our accuracy probably. So our first option here is zero padding for interpolation. So we interpolate the whole range Doppler matrix. And this is basically a sinc interpolation in the FFT domain here. So here on the top left, we can see the actual signal that might have been transmitted. Then on the right, we apply zero padding. So now this signal is 4 times larger than the signal on the left. And then we apply an FFT in both cases. And we can see if we apply the zero padding, we get a lot of more points here around this peak. And through this interpolation, we might get a better estimate than, well, than just this point. We might see that like the one slightly to the left or slightly to the right is better at that point. But it also has disadvantages. We need to calculate a lot of different values here. Therefore, we also addressed the chirp Z transform. So there we just look at a range of interest, and using our chirp Z transform or CZT, we can just look at a small section here of our frequency domain. So to show how this works, I went into the Z domain and I put the points of our FFT here on the unit circle, which are our blue circles. And with the green axis, this is what we get when we apply zero padding. So we get a lot of more points on this circle. But now if we apply the CZT, we can potentially work here in this spiral. So our A is our starting point and our W is basically our step that we go. But if we configure W with unit power, we can also just look at a small section here of the unit circle. And this is how we will use this CZT. And in our comparison here, we decided to use the same amount of interpolation because the interpolation is exactly the same in the end. And this also a similar complexity. So we will apply zero padding with a factor of 16, and this results in a very, very kind of small step size here. Then on the other hand, we mentioned tracking. So we have here 2 reference models. The first one would be our event-based measurement. So either we had just a jump in value, so I just measured 6 meters last time step and 12 meters now. That would mean that, well, we just set the measured value to 9 meters. So just if there's a switch, we put the value in the mid, we estimate the middle value. And if there's no switch, we rely on linear prediction, which we can because of the estimate of our radial velocity. This is very low complexity. It also self-aligns to the measurements if our initial position is not well known, but we need a high reliability of our measurements. Then on the other hand, we applied a Kalman filter. You can see the prediction equation. So the first one is the same one that we just used for the event-based measurement. And then for the velocity and the angle, we predict that it stays because we don't really implement a movement model for these. And with the Kalman filter, we can really nicely combine the predicted and measured value. We get also some inherent noise estimations of the predictions and also of the estimate. But the system is also very sensitive to the estimated process noise and observation noise. So we need to really design good values to have it work well on our system. And lastly, now we combined tracking and interpolation into one system with also comparable complexity of what we just saw. So we coined this the Kalman CZT because this is a Kalman filter where the measurement is entangled with the Kalman values that are calculated. So first we go through the prediction. We calculate here first our prediction value, but also we predict the covariance of our prediction. And we use this covariance to decide on our observation window of a CCT. So how much of my unit circle do I need to interpolate and calculate? So we just use this 3 sigmas rule from a prediction here and to decide on this width. Then we perform the measurement based on our actual measurement values, but this is our prediction, this steers our prediction window, this arrow here steers our starting position. And we perform the measurement and then perform our peak detection. And then lastly, we perform our Kalman filter update step, calculate our estimate, but also calculate here at some point this new observation noise. Then let's look at our results. So you can see here results where we know the initial estimate based on our native resolution range Doppler matrix, which means RDM here, green curve, is just doing the estimation as shown in the first slides. And then if we also add interpolation, we can see that we get from like 1.7 meters RSME down to 10 centimeters. And as said, these interpolations are exactly the same as long as on my CCT window is on my peak somehow, we get the same result. We just get in the first time step, we basically take the RDM estimate as an initialization because we need to we need some part of the system to tell us where we should zoom. Then for the tracking, we also get system performance, not as severe as for the interpolation, but we get down here to like 30, 40 centimeters. And at some point this will equalize to a stable level, which is pretty close here. And also our Kalman filter and our event-based measurement perform very, very similarly. And then lastly, with our Kalman CCT, we can get a lot of improvement here. We are almost at like 3 millimeters precision for our simulated point target. And we are also very, very stable at this level. So it seems like in the first time step, we kind of lock on the target and then we already know where we are, and it doesn't really make sense to make our Kalman window our CCT window even smaller. So this is a lot of gain here, and we're at a similar complexity as with these other algorithms. Then we also evaluated the same values if we know the true initial position. Then, of course, our tracking algorithms perform slightly better at first and then equalize to some type of stable level. So here our Kalman filter is just drifting away a little slower from our true position. But for the other systems, the behavior is not really changed. So that already brings us to the end. So as a conclusion, we had here the scenario for bandwidth limit, limiting our range estimation. And we had 2 options for accuracy improvement. First, using the time correlation between samples, aka doing tracking, or changing the measurement bin size by performing interpolation. And as take-home messages, I can tell you, both improve our estimation accuracy. Still warning with that our tracking is sensitive to the process and observation noise, so fine-tune your filters. And then lastly, our Kalman CCT approach really improved this accuracy further, significantly, at a comparable algorithm complexity. So thank you for your interest in our work and see you in our next talk.